SwayamPrabha. Digital India. Educated India.
In this lecture, we'll be starting how we can find the linearized equation of motion of the aircraft. So let me write the heading. Linearized equation of motion of the aircraft. Before we proceed, let me rewrite the trim flight condition of the longitudinal equation because it will be required while deriving the state space model. So the trim flight condition for the longitudinal motion we had x naught minus mg sine theta naught equal to m u naught dot z naught plus mg cos theta naught equal to m double naught dot and m naught equal to 0. And let me define this equation number 1. Now we'll start to find the part of equation of motion of the original equation, the force equation in the longitudinal motion. Force along the x-axis will start. To begin with, considering forces along in the x-axis or x direction, we can write x minus mg sine theta equal to m u dot plus q w minus r v. Now, if we write this equation in part of form, we can write, so if we substitute here, x equal to x naught plus del x and theta equal to theta naught plus del theta and u equal to u naught plus del u, q equal to q naught plus del q, and w equal to w plus del w, and r equal to r naught plus del r, and v equal to v naught plus del v. So this is basically the first term indicates the reference model, and the second term the part of variable. And if you substitute these terms in the equation 2, we can get, substituting or writing the equation 2 in reference and part of variables, we can write x naught plus del x minus mg sine theta naught plus del theta equal to into d dt u naught plus del u plus q naught plus del q and into w naught plus del w minus r naught plus del r into v naught plus del v. And if you ignore the product of water variables and if you assume the stream flight condition, okay, let me write during stream flight, we know that E naught equal to 0, the side velocity for the reference model will be 0, P naught equal to 0, Q naught equal to 0, and R naught equal to 0, and neglecting the products of disturbances. Here basically the terms like, for example, del Q into del W, or the other terms like del R, del V, some these terms, dot, dot, dot. So we are neglecting these terms because the magnitude of these terms are very small, as these terms, these are small. So after introducing this condition in equation number, let me write equation number 3, yields, we can write x naught plus del x minus mg sine theta naught plus del theta equal to m u naught dot plus m del u dot plus m del q w dot. And we can further write this expression. If you extend this sine theta naught plus del theta, we know that sine a plus b, we can write sine a cos b plus cos a sine b. So if you write in this, if you extend this expression in this form, so we can write x naught plus del x minus mg sine theta naught cos del theta plus cos theta naught sine del theta equal to, we can write m u naught dot plus m del u plus m del q omega naught. Further, we can write x naught plus del x minus mg sine theta naught cos del theta minus mg cos theta naught sine del theta equal to m u naught dot plus m del u plus m del q omega naught. Let's write this equation number 4. Our main motivation is you have to find the expression in terms of water variable form, the rate of change of water variable. And our motivation is uh, how we can neglect or reduce the perturbation with some control. Okay. If you assume further, if you assume further, if you assume the perturbations are small, for this condition we can write cos del theta equivalent to 1 sine del theta equivalent, we can write del theta for the small value of del theta. In this condition, and equation 4 can be yields to be we can write x naught plus del x minus mg sine theta naught minus mg del theta cos theta naught equal to m u naught dot plus m del u dot plus m del q omega naught, sorry, w dot. Here we're going to use the equation number 1, the trim condition of the aircraft, of the longitudinal motion of the aircraft. So if you consider here, if you notice here, x naught mg, x naught minus mg sine theta naught actually mu naught dot. So we can replace here this expression x naught minus mg, x naught minus mg theta naught we can replace by u naught dot, we can replace. So using this equation number 5, using equation 1, equation 5 can be written as, right, mu naught dot plus del x minus mg del theta cos theta naught equal to mu naught dot plus m del u dot plus m del q omega naught. And these two terms can be, both sides can be neglected. So we can write del x minus mg del theta cos theta naught equal to m del u dot plus m del q double dot. So if you notice in this equation, our part-time variable, we wrote the equation in terms of part-time variable basically, and we have to come up the expression. Left hand side should be the del u form and the right hand side should be the list of the part of terms. Okay, we'll proceed. Let's proceed. And here we need to assumption, another assumption. Let me write the assumption. If we align the body axis, body x-axis along the direction of airplane's velocity vector. In that case, we can write W naught will be 0. So this is basically stability axis we can write. So in this condition, equation 6 for the above assumption, equation 6 can be written as, can write del x minus mg del theta cos theta naught equal to m del u dot. Let me define this equation number 7. Now we have to see how this part of force going to generate in the body axis. This is very, very important. And here basically we will come up with the concept of control also. Now let me write the force del x. Because of this del x, the system has been part up to del u form. The velocity has been changed to del u. The force del x is the change in aerodynamic and propulsive forces, because already we have discussed that x actually the total force which is coming from the aerodynamic and propulsive forces. And del x is the change in the aerodynamic propulsive force in the body x-axis or x direction, we can write. And this delta x or del x can be written in Taylor series form and can be expressed by Taylor series in terms of perturbation variable. Perturbation variables. So let us write. So del x will be function of del u, the perturb variable in velocity along x-axis, del w, del q, and del e, delta del e, and capital delta del t. So here if we write, let me write this, and also this expression also you can write del x by del u into delta u plus del x del w. This is how we can write in Taylor series expansion, delta w and del x by del q delta q plus del x del delta e into delta e plus del x del delta t delta t. So these are these terms actually, this is called stability derivatives. These terms actually called stability derivatives. That is, if you look in control theory perspective, these are the basically Jacobian matrix in Taylor series expansion. Okay, let me write here. This is basically Taylor series expansion, this expression. So now let me denote this equation number 8. So here delta del E and delta del T are the perturbation variables in the elevator input and fraction of maximum thrust. Here I should note down. So these are basically delta E, elevator deflection. So this causes to deflect the body from the reference point to different point. And if it is going to control the delta x term, this delta x, then we can say this is the favorable control input to the system, which is going to control delta x, or which can control indirectly. Actually, we are controlling the delta u dot. So how we can make time rate change of delta u to 0 with the application of the delta as this control input and perturbation and the maximum thrust. So we'll be looking while designing the control algorithm. So for the time being, this delta x we can write in this Taylor series expansion, and where delta delta e, del e, and delta del t are the elevator input and maximum thrust, fraction of the maximum thrust, which is going to generate delta x. And the other also Jacobian matrix involved here, due to which the delta x can be generated. Let me write further. Del x, del u, and del x, del w, del x, del q, del x, del delta e, and del x, del delta t represent the stability derivatives. This can be found from the wind tunnel testing, basically, which are evaluated at the steady state value. Basically, these are the matrices if you look, and generally, if you remember, while studying of the state space representation, we considered the Taylor series expansion of the system, of the pendulum system. The value of this expression at the equilibrium point, or the stream values. This is what we have done for the pendulum system. Now, the aerodynamic forces and moment, the aerodynamic forces and moments can be expressed as a function of all motion variables. However, generally we're gonna use almost all variables are involved to generate this force and moments, but we'll be using which contributed most. So we can write, however, in this equations, only the terms that are usually significant have been considered, have been retained. The effect of also we can have another assumption in equation 7, equation 8 actually you can write equation 8. There's another assumption is the effect of pitch rate Q on the x the force, which is basically x naught plus del x, is negligible because they are in the same direction. We can say that.
Yeah.
I mean, we are assuming the rate along the y-axis to be 0. We are assuming, and that's why the effect of the force along x direction will be negligible, and therefore, the above equation, therefore, the equation 8, no, the equation 7 reduces to, we can write del x, del u, delta u plus del x, del w, delta w minus, sorry, plus del x, del delta e, delta I plus del x, del delta t, del delta t minus mg del theta cos theta naught equal to m delta u dot. So this is the expression we are getting from equation 7 and 8. And if you rearrange this expression again, we can write m, if you combine this expression and this expression and this expression, we can write d dt, we can write minus del x del u, we can write delta u minus del x del w plus mg del theta cos theta naught equal to, we can write del x del delta e plus del x del delta t delta dt, and this expression. If you divide a mass of the aircraft on both sides, you can write del delta t minus 1 upon m del x del u into delta u minus 1 upon m del x del w plus z del theta cos theta naught equal to 1 upon m del x del delta e del delta del e plus 1 upon m del x del delta t delta delta t. And if you denote denote xu equal to 1 upon m del x del u, and xw equal to 1 upon m del x del w, and x delta e equal to 1 upon m del x del delta e, and x delta t equal to 1 upon m del x del delta t are the aerodynamic derivatives divided by the airplane's mass. And if you write this, let me define this equation number. This is equation number 9. Equation number 9 can be written as, by the above changes or notations, we can write del t minus xu del u minus x w del w plus g del theta cos theta naught equal to x delta e plus x delta t del delta t. So this is the equation of the force along x direction in the longitudinal motion. And let me define this equation number 10. So this is basically, you can say, the linear model of the system, because these terms are constant, which are part of variable. This is also generally will be assuming this is the, no, here actually this is constant value, this is constant value, these are all constant term. Equation 10 actually the linear equation of the force equation in the x direction. And here we have seen that how the delta u going to change with respect to time. And the equation is in linear form because this xg, xw, these are stability derivatives, and z and cos theta naught and x delta e, x delta t, these are the basically constant for a given flight condition. And these stability derivatives we find from the wind tunnel testing. So now we'll be moving to the next part of the force equation along z-axis, and how we can find the linear form of the force along z-axis. So that part we'll continue from the next lecture. Let's stop it here.